All right, so we're going to go ahead and move forward in Unit 9 with the next section, which is all about solving exponential equations. And when we solve exponential equations, there's two types that we're going to have to solve, okay? And there is the type where we can make sure that both sides of the equation are raised, or let's say are the same exponential base raised to powers, okay? So if we can write both sides with the same exponential base, that's kind of case one. And then what happens when we have two sides of the equation that cannot be written as the same exponential base. Okay, so I'm going to show you both of those today. The reason why we hope that we can write them with the same exponential base is because we have this one-to-one property of exponential functions, which says if we have the same exponential base on both sides, that is only true if our powers are the same. Okay, so what that means is if I had something like 2 to the x equals 2 to the 3. Well, if this is a statement of equality, 2 to the x equals 2 to the 3 would have to mean that x equals 3. Okay, so we're going to use this property a lot, both with solving exponential equations and then also with solving log equations. So we can actually take an equation and put in any exponential base that we want, as long as we have an equality beforehand. Or if we have an exponential equation and we can write it with the same exponential base on both sides, then using this one-to-one property of exponential functions, basically we could just drop those bases and solve the equation that's left over by the exponents. Okay, so this is the good case. This is the easy case. So let's go ahead and look at some. If I look at 7 to the 12x equals 7 to the 2x minus 2, notice I have the same exponential base on both sides. So what I can do is I can just drop those, because the only way that these two things would be equal is if their exponents are equal. So I'm going to drop the 7's and then just solve 12x equals 2x minus 2. Okay, and now that's a really easy equation that we have to simplify, right? So I'm going to subtract 2x from both sides, which gives me 10x equals negative 2, and then I just divide off my 10. Okay? So x is equal to negative 1/5 whenever we reduce. Okay, and the good thing about these problems is because we're solving for an x that is up in the exponent, there's no issues with the types of solutions that we get. It's okay to get negative answers. It's okay to get 0 answers. It's okay to get positive answers. So you really don't have to check your answer when you're dealing with exponential equations unless you just want to. Okay, so if you want to check your answer, all you would do is take negative 1/5, plug it back up in here into the exponent, and make sure that this still creates a true statement. Okay, and you can check with your calculator. All right, same thing on this next one. Notice we already have the exponential bases of 4 on both sides. So because I have 4 to some power equals 4 to some power, the only way that that would be true is if those exponents are equal. So I'm going to go ahead and just drop the 4's and solve 3x equals x minus 5. Okay, so I go ahead and subtract x from both sides, which gives me 2x is equal to negative 5. And then I get x isolated by dividing off the 2. So x equals negative 5 halves. Okay, kind of makes sense. This is our this is our easy case, and so we want to go ahead and practice this really quick before we get into ones that require some extra work. So down at the bottom of the page, there's one for you to solve, this little practice problem. So go ahead and take a minute to do that. And then when you're ready to check yourself, go ahead and unpause the video and we'll see how you did. All right, so let's go ahead and look over this practice problem. Since they both have an exponential base of 18, we can go ahead and drop those 18's, and we're left with the equation negative x equals negative 3x minus 8, and then we just solve it like a regular equation, right? Get x's isolated, divide off any coefficient we have, and here we should end up with x equals negative 4. Okay? All right, so these were our easy cases. These were our, hey, the sides already have the same exponential base and all we have to do is drop them and solve and see what we're left with. Now we're going to look at some where we can still have the same exponential base on both sides, but we have to work for it a little bit, okay? We have to think about how to rewrite things so that they end up with the same exponential base. And one thing I want to caution you on right now is that you cannot change the value of either side of the equal sign, okay? You can rewrite it in a different way, but you cannot change the value. Let me show you what I'm talking about. Here we have 5 to a power and 25 to a power, and we want to be able to write these guys with the same exponential base, okay? Now, some people may say, oh, well, 25, I can get that from taking 5 and just multiplying it by 5, right, or squaring it. But I can't do that because if I were to square this side and not do anything over here, that changes the value, right? I can't multiply by 5 or square this 5 and only do it on one side because that changes the value. So I don't want you to look for the small thing and try to make it bigger. What I want you to look at is look at the larger base and see if you can just rewrite it as a smaller base, maybe raised to a power, okay? So what I'm saying here is we can't just do something to this 5 to make it bigger. That's a no-no. That changes the value. But we can take 25, and since we know that 25 is 5 squared, we can just rewrite it as 5 squared. So I'm going to come down here and rewrite this as 5 squared, and then it still has an exponent on it, right? The exponent that was originally there, x minus 2. So now I have 5 to the x plus 1 equals 5 squared raised to the x minus 2. Now our one-to-one property said we had to have an exponential base on both sides raised to a power, okay? Not a power raised to a power. So before we can drop these 5s, we have to make sure that our exponents are completely simplified, okay? So I'm going to write over here and just say simplify exponents before dropping the bases. Okay, simplify the exponents before dropping the bases. So I want to go ahead and do this. Now remember, when you have a power raised to a power, we multiply powers. And because there's 2 terms within this second exponent here, I have to be sure that I distribute that 2 to both of those exponents. Okay, so I end up with 5 to the x plus 1 is equal to now 5 to the 2x minus 4. And now that I have it written as 5 to some power equals 5 to some power, now I can go ahead and drop those 5s. So I would be left with x plus 1 equals 2x minus 4. And again, now we have a very easy to solve equation, right? We move our x's to the same side. I'm going to subtract 2x from both sides, so I get negative x plus 1 equals negative 4. I'm going to move my 1 over to the other side, which I do by subtracting. So I get negative x is equal to negative 5. And then I want to make sure that this is solved for positive x, not negative x, right? So I can get rid of that negative sign by either multiplying or dividing by a negative. So I'm just going to divide off a negative 1, which gives me x is equal to positive 5. So we go ahead and circle that as our solution, okay? All right, so let's look at another one. This one was pretty easy because all I had to do was rewrite one of the sides. But notice on this next example, I can't write 8 as 4 to some power, right? Like this one was easy because 25, I could rewrite it in terms of the other base. But 8, I can't write that as 4 to some power, right? Because 4 squared gives me 16, not 8. So since I can't write the 8 in terms of the smaller base, then what I want to do is I want to look at both bases and see if I can write them both in terms of a smaller base, okay? So a smaller base that both of these numbers can be written in terms of is 2, right? 8 is the same thing as 2 cubed, and then it has the exponent that was previously on it, which is negative x. And then 4 can be written as 2 squared, right? And then it has the exponent that was I can't say that word, oh my goodness, previously on it, okay? All right, and then remember our little note here, before we can drop the 2's, we have to completely simplify the exponents. And when we have an exponent or a power raised to another power, our operation is multiplication. So over here, 2 times negative x gives me 2 to the negative 3x. On the other side, again, we have two exponential terms out here, so I have to make sure I distribute that 2 to both of these terms. So that will give me 2 to the negative 6 plus 6. And now that I have 2 to some power equals 2 to some power, I can drop my 2's. So when I drop my 2's, I'm left with negative 3x is equal to negative 6x plus 6. And then this is something that I can easily solve, right? I'm going to move my 6 over by adding 6x to both sides. So I'm left with 3x is equal to 6. And then I solve for x by dividing off that 3, which gives me x is equal to 2. Okay? All right, so same idea. We want both sides to have the same exponential base. So if you can modify just one and get them to look the same, great. Sometimes you have to modify both of them to get them to look the same. So there are two practice problems for y'all to try down here. Same exact types of problems, just getting used to having to modify the base so that they're the same so that we can drop them. Okay, so go ahead and pause the video and work those out. If you get stuck or if you finish and you're ready to be checked, unpause it and we'll go over them. Okay? Okay, so here we go. First practice problem. I can write the larger number 64 in terms of the smaller base because 64 is the same thing as 4 cubed. Okay, so I'm going to rewrite the 64 as 4 cubed and then make sure you distribute that 3 to both terms. So that gives you 4 to the 3x plus 6 equals 4 to the x minus 5. And then we can go ahead and drop our 4's because our exponents are completely simplified. So we're left with 3x plus 6 equals x minus 5. And then that's an equation that we can easily solve. So when you finish this out and solve for x, you should end up with negative 11 halves. Okay? All right, same thing with the second one, except this time I can't write 64 as 16 to some power. I can't write it in terms of the smaller base. So I need to find a base that both 16 and 64 can be written in terms of, and that would be 4. We know that 64 is 4 cubed and 16 is 4 squared. So I just replace 64 with 4 cubed, 16 with 4 squared, and then be sure you simplify your exponents before you drop the 4's. Okay, so when I distribute the 3 here, I'll get 9x minus 9. When I multiply 2 and 3x, I'll get 6x. Then I can drop my 4's and just be left with that equation. 9x minus 9 equals 6x, and then solve that for x, and we should get x equals 3. Okay? All right, so what we have done so far is we've looked at problems where the bases on both sides were already the same, so we just dropped them. And then we looked at problems where the bases were not the same, but we were able to write them as the same base, right? So the last thing we have is to look at problems where the two bases that were given cannot be written in terms of each other or in terms of a smaller base where they match, okay? So a little bit different strategy, but not too much worse, okay? So here it says use logarithms to solve the exponential expressions, okay? So we're going to use logarithms either to cancel out the exponential base or to be able to get our unknown out of the exponent, okay? So let's look at a couple here with natural logs first. It says solve for x, round your answer to the nearest tenth. Okay, be sure that you always pay attention to what your problem is asking for in terms of how to round it, because sometimes they'll ask for the tenth, sometimes they'll ask for the hundredth, sometimes they'll ask for 4 decimal places, and it varies from problem to problem. So be sure you're keeping an eye on how your answer should be written so that you're not having to do extra problems based on a rounding error. Okay? All right. So the first thing I want to do is I want this one written like all the others we've done. I want that exponential base isolated. Okay, so what I mean by that is this thing that has an exponent, the exponent is 10x. That 10x is only being applied to this e. There's no parentheses saying that this 7 has anything to do with it. So I want to go ahead and just get rid of that 7 by dividing it off because it's not part of my exponential expression. Okay, so that gives me e to the 10x equals, now you could go ahead and get a decimal here, but I'm going to wait until the end because 12 over 7 does not turn into a pretty decimal. It turns into a decimal that just keeps going and going and going. I don't want to have to write all that mess. So for right now, I'm just going to leave it as 12 over 7. Okay. Now I need to get rid of this exponential base e. And remember, logarithms and exponents are inverses, meaning that they cancel one another out. So I need a log that will get rid of exponential base e. And the only log that will get rid of exponential base e is log base e. And remember, log base e is one of our special logs. That's our natural log. So what I'm going to do is just take the natural log, or the ln, of both sides. Okay, if you do it to one side, you got to do it to the other side. So I'm going to take the natural log of both sides, and what will happen on the left is my ln and my e will cancel. And that will leave me with 10x is equal to ln of 12 sevenths. Okay. Now ln of 12 sevenths, that's just something I can type into my calculator, right? So again, I'm just going to wait till the end to simplify that. Because I have one more step. To get x all by itself, I need to divide off that 10. So I'm going to divide off the 10. So x is equal to ln of 12 sevenths divided by 10. Okay, and now I want to go ahead and plug this into my calculator so that I can get an answer. Okay, now if you're new to using your calculator, make sure you reference your manual, right? We want to do order of operation here, so we're going to do 12 divided by 7, see what that equals, then take the natural log of it, see what that equals, and then divide by 10 so we can see what that equals. So go ahead and punch that into your calculator if you have it handy. You should end up with 0.0538, and it keeps going. Okay. Again, our instructions said to round to the nearest tenth. So if we round to the nearest tenth, that's one decimal place, which is where my 0 is. And notice there's a 5 behind it, so that's going to bump it up to a 1. So we're going to say for this one, this is approximately 0.1 as our solution. Okay. Let's look at another one. Same idea. First thing we want to do, make sure our exponential is isolated. Notice there's no parentheses around the 6 and the e, which means that that negative 5x is only being applied to the e. So I'm going to get rid of the 6 by dividing it off. So I end up with e to the negative 5x is equal to 25/6. Again, I'm just going to wait till the end to simplify it. And then again, I can get rid of exponential base e by taking log base e of both sides. And log base e is our natural log, or our ln. So we're going to do ln of e to the negative 5x is equal to ln of 25/6. Remember, if you do it to one side, you got to do it to the other side. My ln and my e will cancel, and I'm left with negative 5x is equal to ln of 25/6. And then the last thing I have to do is just divide off that negative 5 to get x by itself. Okay. So I have x is equal to, so on this one again, do your 25/6, then take the ln of that, then divide it by negative 5, and we should end up with negative 0.2854 and some more stuff. Okay. Again, we're going to round it to the nearest tenth, which is one decimal place. Here we had a 0.2, but there's an 8 behind it. So that's going to bump this up to approximately negative 0.3. Okay. Are we kind of okay? All right. So we use the natural log on both of these because we had an e, right? And if we have an e and we take ln, they'll cancel. Now, if I didn't have an e here, let's say I had like a 10, right? I had 10 raised to some power, then I would want to use the common log, right? Or even if I had 2 to some power, I could do log base 2 and then use change of base later if I needed to, okay? But what I want to look at now is having more than one exponential expression, having one on both sides, and having one that specifically cannot be written as the same exponential base on both sides. So let's think about this one. Excuse me. If I wanted to solve for x, it's right now stuck in the exponent. And to get something out of the exponent, I need to use a log to get rid of that exponential base, right? So let's think about this. If I were to take log base 5, okay, log base 5 sure would cancel out this 5, But on the other side, I would still have log base 5 of 9, which doesn't cancel out, right? Similarly, I don't want to use log base 9 because even though it would cancel out the 9 on this side, then I would have log base 5 on this side, right? Not helpful. So what I'm going to do is instead of picking a specific log for one base, because I have to do the same thing on both sides, I'm actually just going to use a common log, right? Or a natural log. You can use log or ln. I'll use one of each on each of these examples so you can see because it doesn't really matter. But I'm going to go ahead and just choose to do the common log. I'm going to take log of 5 to the x plus 9 is equal to log of 9x. Now I do realize because I'm using the common log and that's base 10, it's not going to cancel out this 5 and this 9. But I have a method, okay? I have a reason. I'm going somewhere with this. The reason that I went ahead and just took a common log is because anytime you have a log, any log, we can use that property that says that our exponent on that inside number of the log can come down as a coefficient. So I'm using this log basically so I can bring down these exponents because that's where my unknown is that I'm solving for. So when I bring these down, now this one has two terms, so I want to bring it down with parentheses. I have x plus 9 times log 5 equals x times log 9. Okay, so this may not look better, but it actually is because we're solving for x, and by taking the log of both sides, we were able to take our x's out of the exponents and bring them down as coefficients. So now I should be able to get all of my x terms on one side, my non-x terms on the other side, and solve for x. Okay, now notice here, this is an x term because it has an x on it, right? But over here, my other x is stuck inside this quantity that's being multiplied by log 5. So to get that x by itself, I need to go ahead and distribute this. So I'm going to distribute log 5 in here to each of these terms. Okay, so that's going to give me x times log 5 plus 9 times log 5 is equal to x log 9. Okay. So all I did was go ahead and distribute this into both terms so that all of my terms are now separated. So now it's really easy for me to see, well, I have a log term here and I have a log term here. Or sorry, not a log, an x term. I have an x term on both sides. And if I'm solving for x, I need to get all my x's together. So I'm going to move this x log 5 to the other side. Since it's positive over here, I can move it by subtracting. So I'm going to subtract x log 5 from both sides. That way it will cancel. And I'm left with 9 log 5 is equal to x log 9 minus x log 5. Notice I did not combine these. This does not become log 4, right? These are like terms in that they both have x's, but they're not like terms because their logs do not match. And if the log numbers do not match, I can't combine them into one term. Okay, I can just write them side by side. So notice, now I have my x terms on the same side. Now I want to get x by itself. And the only way to get x by itself when it's stuck inside of two separate terms is to factor out that x. So I need to take the x out, which will leave me with log 9 minus log 5. 9 log 5 here. Okay, so all I did is factor out that x like a greatest common factor. Now that I have that x factored out, when it's written side by side with a quantity, that's multiplication. I can undo this multiplication by dividing. So I'm just going to divide off this hideous mess here that I no longer need. Okay, whoop. But if I divide it off on the right, I also have to divide it off on the left. Log 9 minus log 5. Okay, so now x is just equal to this big mess. Okay, so I'm just going to rewrite it over here. So x is equal to 9 log 5 over log 9 minus log 5. Okay, now this is not something that can be simplified by canceling out logs or anything like that, but I should be able to simplify it on my calculator. Now, if you have a very basic calculator, you're probably going to have to store your answers. So if you're not sure how to do that, look it up on your manual, okay? But most calculators have a store button where you can take whatever numbers on the screen and store it like in one of these number buttons. So you may have to do like the bottom and store it, and then do the top and then divide it by, and then, you know, like recall that stored value. Okay, so if you need help on that, please look to your manual, or, you know, you're welcome to reach out to me. If you have a calculator like this one, you should be able to do all of this in one step. Okay, the only thing you have to remember when you do this all in one step is that you have to use parentheses showing this is everything that's on top, and then on bottom, this is everything that's on bottom. Okay, so in other words, I'm going to use a parenthesis to say, okay, this is where the top or the numerator starts. I have 9 log 5, and then I close that parenthesis to show that's the only thing inside my log. And then I'm also going to close the parenthesis to show, and that's all that I have on the top. So 9 log 5, that's my whole numerator. And then I'm dividing that by, now I want to enter the bottom. I'm going to start by using a parenthesis to say this is the start of my denominator. And my denominator says to do log 9. Okay, and I'm going to close parentheses to show 9 is the only thing inside of this log. And then I'm going to subtract log 5. So log 5. 5 is the only thing inside this log, so I'm going to close that parenthesis, and then I'm going to close the other parenthesis to show that is the end of everything that's on the bottom here. Okay, and then hit enter. So we end up with x is equal to 24.64319 blah 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 blah, right? And again, our instructions at the top of this page asked us to round to the nearest tenth. So that is the nearest you know, first decimal place, right? So we're going to go ahead and say this is approximately 24.6. Okay? So a little bit tricky. We're solving for x because we cannot write these two exponential bases and the same base, then we just take a log so that we can bring those exponents down. So once the exponents are down, we make sure every term is multiplied out by distributing any logs we have. And then once all of our terms are multiplied out, we move all the x's to one side, divide off the x, or sorry, factor out the x, and divide off what's left over. So let's look at another one like this, okay? Just so we get one more look at it, and then I'll let y'all try one, okay? Or a couple maybe. All right, so 3 cannot be written in terms of base 5. 5 cannot be written in terms of an exponential base 3. So we're at an impasse here, right? We cannot create two bases that look the same on this problem. So I do want to use a log so that I can bring those exponents down to the front of the problem, right, as a coefficient. Now, again, I could use log. I'm going to use ln here just to show it doesn't really matter which one you use. I also personally prefer to use ln just because it's a little bit easier to write. Takes up less ink, right? Or pencil. All right, so I'm going to go ahead and take ln of 3 to the 2x minus 3, and that's going to be equal to ln of 5 to the 4x plus 5. So now that I have a log, whether it's a common log or a natural log, as long as I have a log, we have that property that says we can bring our exponents down as coefficients. Okay, now notice both of these have more than one term in the exponents. So when you bring down more than one term to be multiplied, we need to put parentheses around it. So this is going to look like 2x minus 3 in parentheses times ln 3 is equal to 4x plus 5 in parentheses times ln 5. Okay. And then just like we did on the last one, I can't get these x terms together the way it's written right now because it's stuck in these parentheses. So we need to go ahead and multiply this ln 3 and this ln 5 so that we have terms that are all distributed out. Okay, so I'm going to distribute ln 3 into both of these terms and ln 5 into both of these terms. Okay, so what that's going to look like is 2x ln 3 minus 3 ln 3 on the left-hand side. On the right-hand side, I'm going to get 4x ln 5 plus 5 ln 5. Okay, so now that everything is distributed out, I should now be able to determine which of my terms have x's and need to be on the same side. So notice here I have a 2x ln 3, that one has an x, and I have a 4x ln 5 on the other side. So I want to get these x terms on the same side so that I can factor out the x like I did on the last problem. Okay, so I'm going to move this 4x over here to this side. So I'm going to subtract 4x ln 5, 4x ln 5 to move that one. So I have 2x ln 3 minus 4x ln 5 that I just moved over, minus 3 ln 3 that was already there, right, just bringing it down, is equal to 5 ln 5. So all I did was move this 4 ln 5 term over to this side. So now our x terms are on the same side, but I also have this extra term here that doesn't have an x. So it doesn't need to be on the x side. I'm going to move it over to the right-hand side to be with the other non-x term, right? So I'm going to add 3 ln 3 to move it over. So now I have 2x ln 3 minus 4x ln 5 is equal to 5 ln 5 plus 3 ln 3. Okay? Whew! So we have all of our x terms on the same side now. Now we just need to get that little x isolated, which is stuck inside those. Now, one of my in-class students asked me, well, don't we want to pull out the 2 also because that has a greatest common factor of 2? You could pull out the 2, but remember our initial, or not our initial, our end result here that we're looking for is to get x all by itself. So I don't really want to pull out a 2 with the x because then later I would have to divide that 2 off to get x by itself. So I am only going to pull out the x, okay? And that's going to leave me with 2 ln 3 minus 4 ln 5. And now that I have the x factored out, I can go ahead and get rid of this whole quantity that's stuck to the x, right? It's stuck together like glue with multiplication. So to undo multiplication, we're just going to divide it off. 2 ln 3 minus 4 ln 5. So on this side, we have to divide by 2 ln 3 minus 4 ln 5. Okay. So I'm going to go ahead and write out what that looks like. 5 ln 5 plus 3 ln 3 all over 2 ln 3 minus 4 ln 5. Woo! Right? Okay, so now we have it all written out. Now all we have to do is be able to punch this into our calculator. Okay, again, I'm going to use this one. This is kind of the common one that most people have and use. So we want to make sure that we use parentheses to show the starting and ending parts of the numerator and the denominator. So I'm going to start by opening a parenthesis for the numerator. This is where the top starts. And we're going to do 5 times the ln of 5. And 5 is the only thing inside this ln. So I want to close that parenthesis and then add 3 times ln 3. So ln 3. 3 is the only thing inside this ln, so I'm going to close that parentheses, and then I'm going to close the original parentheses to show that is everything that's in the numerator. Okay, that's the whole numerator. Now I'm dividing that whole numerator by the whole denominator, so I need to open up a new parentheses to show everything that's in the denominator. So everything that's in the denominator, it starts with 2 ln 3. Notice 3 is the only thing inside this little ln, so I'm going to close the parentheses there. Minus 4 ln 5, and 5 is the only thing inside these parentheses. Oops, I forgot to type my 4 in. 2 ln 3 minus 4 ln 5. Okay, 5 is the only thing inside these parentheses, so I'm going to close it, and then I'm also going to close the parentheses to show that's the end of everything in the denominator, okay, and then just hit equals. So this comes out to x is equal to negative 2.6749 blah blah blah, and then we're going to round it to the nearest tenth, which is 1 decimal place, which is 2.6. Since there's a 7 behind it, that's going to bump it up. So this is approximately negative 2.7. Okay. All right. So quick rehash on both of these problems. If the two bases cannot be written the same, okay, if you only have one exponential base like these, then you can just use whatever log you need to get rid of that one base. But if you have two exponential bases that cannot be written the same, then you have to use either a common log or a natural log to bring down those exponents so that you can solve them for x as x terms. Okay? All right, so that is the end of this lecture. But on the next page, there are two practice problems for you to attempt, okay? And even though number 2 is multiple choice, and I do want you to select the multiple choice because this is what some of your homework problems will look like, I also want you to go ahead and work it out and give me a decimal answer just so that I know you know how to calculate this correctly in your calculator, okay? And it doesn't say here, but let's go ahead and say round to the nearest tenth, just because that's what we did on the other page. Okay. All right. So go ahead and pause the video and work on those two. If you get stuck and need help, or if you finish and need to check yourself, then go ahead and play the video and we'll see how you did. Okay. So on our first practice problem, first thing we want to do is isolate that exponential, meaning get rid of the 4 because it does not have an exponent tied to it. So we divide off the 4, which leaves us with e to the 7x equals 17 over 4. And then to get rid of that exponential base e, we take log base e of both sides, which is our natural log. Okay? When we take ln of both sides, the e and the ln cancel on the left-hand side, leaving us with just 7x that was in the exponent is equal to ln of 17/4. Then to solve for x, all we have to do is divide off that 7. So we divide off 7. This is what our answer would look like if Newton had you stop there and wanted a multiple choice. It would probably look something like this. But we want to go ahead and work it out and get a decimal answer. When you round it to the nearest tenth, you should end up with 0.2. Okay, if you need more time on that, feel free to pause the video, but I'm going to go ahead and move on and look at number 2. So on number 2, these two bases cannot be written with the same exponential base on both sides, right? So I'm going to go ahead and take ln. Now, if you took log, that's okay. Either one is fine. You just need a log in front of both of those terms so that we can bring down the exponents, okay? So if you took log, that's okay. So I did ln to bring down this x. I did ln to bring down the x plus 1. So I end up with x ln 2. On this side, I need to distribute that ln 3 into both terms. So I'll get x ln 3 plus 1 ln 3. Or you can just write this as ln 3. Okay, either way. I need to get my x terms on the same side. I have one over here and one over here. So I'm going to subtract this guy to move it over to the left. These are not like terms because they don't have the same number inside the log. So I just write them out side by side. X ln 2 minus x ln 3 equals ln 3. And now that I have my two x terms on the same side, I can factor out the x. Okay, when I factor out the x, that's going to leave me with ln 2 minus ln 3. And now I can get x by itself by just dividing off that quantity that I don't need. So when I divide that off, I'll be left with ln 3 over ln 2 minus ln 3. So we can tell by just that answer that our correct solution choice over here should be the second one, right? So in Newton, that would be your answer, and then you would stop there, okay? But it is also possible that they'll have you work it all the way out. So in your calculator, when you enter this in, you should end up with negative 2.709 and some more stuff. And when we round it to the nearest tenth, that gives us a negative 2.7. Okay. All right, so that is the end of this solve exponential equations section. So you should now be able to complete that assignment in your Alta Newton homework. And if you have any questions, please let me know.